Have you ever wondered how your computer processes information so quickly? The magic happens inside the CPU, the brain of your computer, but how does it really work? So let's break it down in a simple way. CPU stands for Central Processing Unit. It's the core component of any computer responsible for executing instructions and performing calculations. Think of it as the conductor of an orchestra, directing all the components of your system. Control Unit CU. This part is like the boss, fetching instructions from memory, decoding them, and telling other parts what to do. Arithmetic Logic Unit ALU. This is the math wizard. It performs all the calculations and logical operations. Registers. These are tiny, super fast memory storage areas that hold data the CPU needs right away. The cache. A small but fast memory inside the CPU that stores frequently used data to speed things up. Now let's see how a CPU actually processes instructions. It follows a three-step process called the fetch, decode, execute cycle. Step 1, the fetch. The CPU retrieves an instructions from memory. Step 2, decode. The control unit translates the instruction into signals. Step 3, execute. The ALU or other parts carry out the instruction and the result is stored or sent where needed. Let's take a simple example. You press a key on your keyboard. Here's what happens inside your computer. Fetch. The CPU gets the instruction from memory that says a key was pressed. Decode. The control unit figures out which key was pressed. Execute. The CPU tells the display to show the letter on your screen. So this entire process happens in just a fraction of a second. CPU speed is measured in gigahertz. A gigahertz means a CPU can process more instructions per second. Modern computers also have multiple cores, meaning they can handle multiple tasks simultaneously. So, to recap, the CPU is the brain of the computer. It fetches, decodes, and executes instructions in a loop. With faster speeds and multiple cores, CPUs continue to evolve, making computers more powerful than ever. The evolution of the CPU from past to present. The CPU or Central Processing Unit has come a long way since its invention. From room-sized machines to the tiny chips in our smartphones, CPUs have evolved dramatically. But how did we get here? Let's explore the history and evolution of the CPU. The journey of the CPU began in the 1940s with the vacuum tube based computers like the ENIAC. These machines were massive, slow, and consumed enormous amounts of energy, but they paved the way for the first true CPU. In 1971, Intel introduced the 4004 processor, the world's first commercial microprocessor. It had just 2,300 transistors a, and a clock speed of 740 kilohertz, millions of times slower than today's CPUs. The late 1970s and 80s saw the rise of 8-bit and 16-bit CPUs like the Intel 8080 and Motorola 68,000, making personal computers possible. These chips powered machines like the Apple II and early IBM PCs. The 1990s brought the Pentium series, revolutionizing performance with superscalar architecture. Soon after, the gigahertz race began, with companies pushing CPU clock speeds past 1 gigahertz by the early 2000s. As single-core CPUs hit performance limits, multi-core processors emerge, dual core, quad core, and now CPUs with dozens of cores allow for multitasking and high performance computing. Today, CPUs are more powerful and efficient than ever. With advancement in AI, quantum computing, and energy efficient designs, the future of CPUs is bound to be even more exciting. From room size computers to the chips in our pockets, the CPU's evolution has shaped the digital world. So, what do you think the future holds for processors? Understanding GPUs, how graphics processor works. Have you ever wondered how your computer generates stunning graphics or powers AI applications? The secret lies in the GPU, the graphics processing unit. But how does it work? So let's start. A GPU is a specialized processor designed to handle graphics, rendering, and parallel computing. Unlike a CPU which processes a few tasks at a time, a GPU can handle thousands of tasks simultaneously. This makes it perfect for gaming, video editing, and even AI training. GPUs work by breaking down images into small parts called pixels. These pixels are processed in parallel to create smooth and detailed graphics. This is why GPUs are essential for high performance visual applications. There are two main types of GPUs, integrated and dedicated. Integrated GPUs are built into the CPU and are great for basic tasks. Dedicated GPUs, on the other hand, are separate hardware components designed for high performance applications like gaming and 3D rendering. GPUs are not just for gaming, they are used in creative industries for video editing, in AI for deep learning, and even for cryptocurrency mining. Their ability to process massive amounts of data quickly makes them crucial in various fields. From simple 2D accelerators to modern ray tracing powerhouses, GPUs have evolved dramatically. Today's GPUs, like the NVIDIA RTX and AMD Radeon series, use AI-powered rendering to create realistic lighting and shadows. GPUs have transformed how we experience technology from gaming to AI. As advancements continue, the future of GPUs look more powerful and efficient than ever. Understanding SAP1 operations and programming. So, ever wondered how a simple computer processes information? Meet SAP1, or Simple as Possible 1, a basic model that helps us understand how computers work. In this video, we talk about down SAP1 operations and even write a simple program. SAP1 is a basic computer model used for learning digital logic and computer architecture. It consists of essential components like the program, counter, PC, memory instruction register, and ALU. These parts work together to execute simple instructions. SAP1 follows the fundamental fetch, decode, execute cycle. Let's go through each step. Fetch. The program counter sends the address to memory and the instruction is retrieved. The instruction registered interprets the fetch instruction. Execute. The control unit directs the ALU or other components to perform the instruction. So the cycle repeats, allowing SAP1 to process instructions step by step. SAP1 has a small instruction set, making it easy to understand. Let's take a look at some key instructions. LDA, or load accumulator, loads a value from memory into the accumulator. The ADD, or addition, adds a value from memory to the accumulator. The sub, or the subtraction, subtracts a value from memory from the accumulator. The out, or the output, displays the contents of the accumulator. The HLT, or the hold, stops program execution. Now let's write a simple SAP1 program to add two numbers stored in memory. LDA14 load value from memory address 14 into the accumulator. ED15 add value from memory address 15 to accumulator, the out, display the result, and the HLT step execution. So this program retrieves two numbers, adds them, and outputs the result. So we can use SAP1 simulator to see our program in action. Watch as the instructions execute in order, updating the registers and outputting the result. SAP1 is a great way to understand how basic computers operate. By learning its architecture, operations, and programming, you gain fundamental knowledge of computing. So that's it. Thank you for listening.